Sketch the region enclosed by the given curves, decide whether to integrate with respect to x or y, and draw a typical approximating rectangle, label its height and width. Then find the area of the region. We have y equals x squared and y equals 4x minus x squared. Quick sketch. Because I have two functions of x, it will make sense for us to set up an approximating rectangle that's vertical. This rectangle here has a width of delta x. Then that tells me that I'm going to integrate with respect to x. The area here is then going to be the integral. And before I fill all this out, I got to figure out what the limits are. For the limits, I just need the x coordinates of the points of intersection. It looks like they're going to be 0 and 2, but I don't want to just guess at it. So I'm going to set the expression that defines the first function, x squared, equal to the expression that defines the second function, 4x minus x squared, and then solve for x. And look, it's 0 and 2. All right. Then I need to set up as my integrand the larger function minus the smaller function. And in this interval, we have the larger function is 4x minus x squared, and the smaller function is x squared. And don't forget, parentheses, because I have a multi-term integrand, and dx. That dx right there represents that delta x. Without it, you don't actually have an area. The actual integration is pretty straightforward. Using the power rule after collecting like terms and then evaluating at the endpoints of our interval, we get that the area is equal to 8/3. I'd like for you to do this next one. Sketch the region enclosed by the given curves and find its area. The region is enclosed by x equals y to the fourth, y equals the square root of 2 minus x, and y equals 0. You're going to have to decide whether to do this in terms of x or y. Start with a picture, give it a shot. Come back when you're done. I didn't get to the end, but I wanted to make sure that we agree on the setup here. So x equals y to the fourth is kind of like a flattened parabola on its side. And then y equals the square root of 2 minus x is going to be a square root function that's been flipped and shifted, right? And then y equals 0 is, of course, the x-axis. Given this region here, I don't want to set it up so that I'm going to have a blue function for one part of the integral and then a purple function for the other part of the integral. And that means I'm going to do a horizontally oriented representative rectangle. And that means I'm looking at a delta y instead of a delta x, which is totally fine. That tells me, though, that when I'm finding my limits of integration, I need everything in terms of y. So I took this equation, y equals the square root of 2 minus x, and substituted y to the fourth in place of x, and found that y was equal to plus or minus 1. Of course, y squared plus 2 gives me no real solution. And we can see in our picture that we're looking where y is positive. So my limits of integration go from 0 to 1. And then here, the purple function needs to be in terms of y. And so I took y equals the square root of 2 minus x, solved it for x. And now I have 2 minus y squared minus y to the fourth. All that times dy. That's my integrand. If you didn't already, go ahead and finish it out. I'll just wait a beat so you can pause it and then come right back. And after using the power rule and evaluating at the limits, we get 22/15.